Hello everyone, I'm Vicente or Vince. You probably won't know me, but I'll be talking about a subject I think is very close to a lot of your heart, is heat flux measurement. But I'll be talking about it with a little bit of a twist because I'm coming from the perspective of a material scientist, so my background's not in building physics at all. So I hope it's of interest to you guys. So a bit of background, and I will ask for a little bit of audience participation because I know it's last talk before the caffeine hit resumes. Does anybody recognise this house? Been to see it? I'm doing a bit of market research for myself here. So this is the Vector house located at Energy House 2.0 that we built back in 2023. And we built this with the intention of having the team over at Energy House assess the performance of this kind of rapid build, low carbon construction method. And we put a lot of effort into making the house look really nice and lovely and pretty, only for Grant to come in and absolutely cover it in sensors and tape and electronics and wires and all sorts. And us being very kind of naive about your world, the world of building physics, we didn't quite understand just how complex it is to kind of derive values for kind of the performance of the thermal fabric. And it was a really cool experience for us to see kind of firsthand what some of the challenges and kind of frustrations were there for the academics trying to kind of use these devices and draw data out. And so just seeing that photo and then thinking about kind of the challenge ahead, and this is all kind of in the UK context, but it's massive, I think, globally. You see that the technology is not there for mass deployment in any way, and this is slowing down things that need to happen. So this is just the example of retrofit, but there's no net zero without emissions reductions. There's not sufficient, there's not a credible pathway to that. And so we need to do a lot of retrofit, but if we can't properly, and I'm preaching to the choir here, if we can't properly measure it, then we can't validate it makes it difficult to fund. And there's a lot of other kind of tangential issues as well around speed and also the kind of the potential for AI in the sector, which was mentioned earlier as well. And so we took a look at kind of what technology was being used in the sector at the minute. Hands up, have you used one of these? Hey, I think this is probably the most popular one. This seems, from my understanding, seems to be the gold standard of what's used in the sector. Quite a kind of a high-end plate. And then at the last conference, we had someone from Echo come and use this sensor. Has anyone used this sensor since? Right, we've ordered one, but it's not come yet. So it's slightly cheaper, slightly smaller. Online, I've seen that you have these excellent plate and metal plates. Anyone use any of these more flexible ones? Yes, about those. And then at the low end, the cheapest kind of heat flux sensors we could find were these American company FluxTech ones, which are screen printed metal link. Any experience with those? A couple of hands as well. And so this is obviously the sensing component, but then, as you all well know, there's the measurement that comes around it, and there's kits from people like PTS who are here today, where you get sensors packaged up with loggers, thermocouples, maybe some software in the background as well, and you're running into the thousands of pounds. And so for any kind of mass deployment, this, to me as an outsider, feels very complicated. It feels very expensive. And so we start to have conversations with these guys and others about what would be like an ideal solution. Like where are we trying to get to? Where are we trying to push this technology? And the list of requirements is quite long. So this is not just switch something out for something else, make this, etc. And most importantly, there's a big focus on you need to make things cheaper. And our background being in the kind of the materials and the graphene ecosystem in Manchester, we thought this would be a nice opportunity to kind of bridge across the kind of Irwell that divides the Energy House 2 facility and our labs over at the Engineering Innovation Centre, and try and collaborate on this project and try and do something interesting. So we were going to have to build a thermopile because all heat flux sensors are differential thermopiles. Quick 101, you've got your thermocouples, so you've got two unalike metals. You put a temperature across them, and then you get a voltage, a potential difference generated due to the Seebeck effect. If you arrange these in series, you get thermopile. If you put that thermopile and you've got adjacent junctions on either side of a known substrate, of a known thickness and thermal conductivity, you can figure out the heat flux due going through it. This is the figure of merit. I'm sure you guys know this maths way better than I do, but the way I look at this, I see, okay, if I want to get my sensitivity as good as possible, I either need a thick substrate with a low thermal conductivity, I want lots and lots of junctions tapped in, and I want materials with a high seebed coefficient, delta. And so we started to have a think about practically how we could do this. And I mentioned my background's in graphene, so here I'm not studying ounce, I'm studying a nanoflake there. And all you need to know for graphene in this context is that it's a material that we can print, similarly to how Flux Tech do their sensor with printed metallic inks, at lower costs. And we can formulate it with different metal additives in order to do formulations with different seebed coefficients. So essentially, the proposal that we laid out was, let's transition this printed electronic stacks, which is at the lower end of the price range, over to these carbon-derived inks and see whether we are able to kind of drop the price that way. So we thought it was a really cool project, involved a couple of universities who spent a lot of time writing a bid, and then Innovate UK rejected it. I was like, so then we changed the title, changed a few other things, did some tweaks, and the second time we were lucky, thank God. But yeah, you've got to talk about your failures as well. And so we knew that we wanted to have this advanced materials element, we wanted to involve these building physicists. However, as you saw from before, this is not the whole ideal solution, there's a big part to it. One comes around like the manufacturing of it, and so we brought in a partner, Printed Electronics Limited, who are experts in printed electronics and scaling and making lots of those devices and getting high yields. And we brought in a Tyrrell Systems, who are down the road from us in Lee, to do the firmware engineering, electronic engineering, and the kind of smart building side. And then when you're kind of negotiating all these different actors, you've got quite a complex R&D project here with lots of expertise. Things can kind of slow down in bits, and we've got a very tight time frame and a very tight budget. And so we also involved some thermoelectric modeling in COMSOL as well to try and accelerate development cycles and make sure that every sensor we made contributed to kind of the progress of the project. One of the challenges of actually doing it in practice is that when you're trying to formulate a new thermoelectric ink, you're balancing the electrical conductivity of the ink with the seebed coefficient, and often those go in opposite ways. And then even if you get those in the right balance, you'll actually need to be able to print your ink and print it at a high enough yield to be able to mass manufacture to hit those price points. This is really difficult to do, but luckily the inks that we started off with proved the concept, so that we knew this could work, and then we did a huge amount of formulation, and you see in these graphs, every single one of these is a different formulation, where we were pushing this seebed delta as far as we could while still retaining good electrical conductivity and good printability. Then on the CAD side, what we did was, and I presented to COMSOL about this, was rather than use kind of traditional CAD software, we completely scripted all aspects of the manifold. So this is a fully parameterized design done in a program called CAD Query. What's nice about this is that it means essentially the computer can generate different printed track designs, different thicknesses, etc. I don't have to go in and manually make each one of those doing it at the start of the project. This is nice because then you can connect this via an API through to COMSOL. So you can have a computer generate a sensor, you can have COMSOL test the sensor, and you can feed that data back. So you can run a DOE and have basically your computer start generating hundreds of designs and testing them, and then we can validate as we print them. So this is really helpful in kind of accelerating the development cycles in a project that had kind of a lot of complexity around it. This is what it looks like to print. So over the project, we printed about 250 individual sensors. This is just one layer, and then you can do all sorts of flip it around, do different materials, etc. And then because we don't have all the best kit in the world, we used a thermal conductivity measurement kit to get a rough idea of the performance of each one, and that's kind of how we progressed. Once we were happy with the sensor, and I'm not going to show you the design because it took us a very long time to get there, we've not quite protected it yet. We went back into the vector house and we basically placed them alongside some Heat Flux plates, some Flux Tech plates, and some electronics on our end with the kind of standard loggers, and just tracked performance against these commercial alternatives. In parallel to that, the IoT electronics are being developed. What we looked to do was take an existing multi-sensor box that kind of was used by Tyrrell and enhance it with the capability to do heat flux measurements and correctly kind of send those over the gateway through to the cloud, for which we're using a kind of proprietary platform. And in the end, we get to where I'm at today, which you will be able to see at the coffee break just next door, because we've set this up here as well, where we have a heat flux plate connected over to what is the logger, but also doing a lot of multi-room measurements through to the gateway through to the cloud. So that's all working now. This is all done in the space of 18 months, so we're really happy with this kind of alpha build, which is where we're at the minute. Is it any good? Not going to tell you yet. Initial trials show this strong tracking. We think we're quite competitive in terms of sensitivity. We're not at hooks, but we're above the current printed sensors on the market. What's most important is we're very confident in achieving this magnitude reduction in cost. What we've done is we've commissioned Energy House to do a thorough testing of these sensors and benchmark them against the competition. So we hope to have that data to share with you soon in the form of kind of a data sheet for the device. And we've got field trials due this winter in houses to try and see it out on the field. From you guys, I'd love for you guys to have a go at it as well. We're hoping to have sensors to send out by the end of the year. You're welcome to come find me afterwards, or just scan that QR code there, or log on the website and send your email. I think that's probably 10 minutes, so I'll leave it there. That's perfect.